So now if we're solving for n, okay, the first thing that I'm going to do is multiply both sides by this, because again, this goes back to what we were talking about earlier. Once we get to this point, it's all about algebra. The science of it is done because we're able to identify each variable as per the equation. Once we do that, the science then transcends into math land. So all we're doing is trying to solve for the amount of oxygen that is remaining in the balloon, right? Okay, so let's go ahead and start by multiplying both sides by 303 kelvins, okay? Now, something beautiful happens whenever we do that. Now, because obviously it's going to cancel out on this side, because this is where we're moving the 303 kelvins from. We're moving it from the right. But when we bring it over here, if you remember, we had to keep our pressure and our temperature the same because the problem, number 6, did not say that it changed. The only thing that changed was our volume and the amount of gas in the system. That's it. So when we do that, both of our 303 kelvins cancel out because they're both on both sides. So we say bloop, bloop, right? And if we rewrite this problem to make sense out of this combobulation, we can go ahead and say 1 times a number is that number. So let's go ahead and get rid of that 1. And we have 5.75 liters over 0.922 moles, right? Is equal to, and again, 1 times a number is that number, 3.25. And then we have over N2, right? Okay, now we can go ahead and just do the math in this, right? We can say on the left side, we say 5.75 divided by 0.922 gives us 624. 24 liters per mole, right? And this is 3.25 liters over N2. Okay? Now, if you remember the portion of algebra, when you have a problem where you have where you have a number being divided by a variable is equal to a number, you can simply swap these two. And let me rewrite that. We have a little space here. So all we're doing at this point, again, is nothing but algebra. We swap these two. We say N2 is going to be equal to 3.25 liters divided by 6.24 liters per mole. Right? Let's do the math on that. And I left those units there so you can see that obviously when you divide, the units flip. So you end up being left with moles. And so that's one way to check your work to ensure that you're headed on the right path. And so if we're just looking at our units are going to line up so that we're left with moles, so we must be on the right path. 3.25 divided by 6.24. And that gives us 0.521 mole of O2 gas in system, right? 0.521, okay? But we're not done because the question also asks us how much leaked out of the system, right? So this tells us how much is remaining. So when we think about that in terms, we know that this is now the change, right? This is the change. This is what's left in the system. We know what we had in the beginning, because if you look back up here, we found that the 29.5 grams of oxygen, when we converted it into moles, it gave us 0.922 moles. Then it went from 0.922 moles to 0.521. So to figure out how much leaked out, all we have to do is subtract 0.521 from what we started out with, which is 0.922 moles. So let's do that over here. In this space, we have this free space over here. So let's go 0.922 minus 0.521. And let's do the math on that. Let's see what that is. 0.922 minus 0.521. And we get 0.401 moles leaked out. Okay, so let's this is a lot of madness going on in this corner, but just so that we isolate it, that you have it here. Now, it's just as simple as that. This is what's found to be left in the system, because everything involving this calculation here is telling us what's inside a system. The only time, anytime that you're going to be questioned to find out how much leaked out, it will involve you subtracting what you find, what's left in the system, from what you started out with. And that will always be how we determine what leaked out. Okay? Now, just to briefly mention, sometimes your professor or your teacher will ask you to give you the grams, to give them the grams. What is the grams? And again, you already know how to do this. We went over this tons and tons and tons of times last semester. But just a refresher, we would take that 0.401 grams of O2, or moles of O2, and we would convert that to grams. And anytime you're converting moles to grams, you're going to be multiplying by the atomic mass of that compound. In this case, it's O2. We know that 2 times 16 is 32 grams. So we would take 0.401 grams and multiply it by 32 grams of the diatomic molecule of oxygen, which is O2, and that would give us the grams that leaked out. Okay? All right, and that's it, buddy. It's tedious, it's long, but it's simple, provided that you understand when to pull out this equation. Whenever you see that it is giving you an initial and a final, then you know that you need to pull out this particular version of the ideal gas law.